We're continuing down the performance road of Accumulo, and next we have Adam Fuchs, CTO of Squirrel.
All right, don't clap yet. You might not like this stuff. I don't know. All right, thanks. So I wanted to give a talk on some performance modeling that we've done lately. And I think if you saw Chris McCubbin's talk just before this, I think he introduced kind of the general performance modeling approach very well. So he set me up for this. We're going to look pretty deep at some of the Accumulo internals here. And I took a poll around the office to see if anybody had good ideas of, how do we make these deep, really difficult internals of Accumulo accessible so that everybody in the audience is just going to completely get it through, great analogies. And I think was it you, Mike Allen, or was it, it was a different Michael in our office, but basically he said, cat dog. All right, so everybody gets cat dog, right? All right, we're going to look at how does Accumulo work on the right pipeline. We're going to take that to discuss basically some of the performance challenges around that, and then we're going to conclude with some steps that have been taken that are going to improve it, and some additional steps that we need to do in future development of Accumulo, and things you can do in your application to make it go fast. So it's going to be a talk for everyone here. It'll be great. All right, so Accumulo, what does it do? Accumulo stores sorted key value pairs. Right, and they're also, they're partitioned, they're atomic. Oh, there's a bunch of details. We don't really need to focus on that. We're storing sorted key value pairs. Right, key on one side, value on the other. Sometimes we group these together and we get some mutations here. So there's multiple values associated with the same row key. We're going to use these, and out of these key value pairs, we group things into tables. All right, so here I've got a bunch of key values lined up. They're in sorted order. You can't tell because they all look alike, but they're actually sorted there. Take my word for it. So I've got table foo and table bar here. And in fact, in order to divide and conquer, we split these up. So we'll take a portion of those keys, and table foo will become two tablets, foo rows A to M and foo rows N to Z. Likewise, bar gets broken up perhaps on a different row split. And then those tablets become units of work that we can distribute through a cluster. And associated with those tablets, we have metadata. The metadata themselves are just key value pairs written into a metadata table, which itself is broken into tablets. And we store those in a root tablet. And it's not cat dogs all the way down. We actually have just this limited 3-level hierarchy here, where Zookeeper keeps track of scooping up after all of these cat dogs. All right, so that's basic organization of Accumulo. Whoops, go back here. Go back. Okay. Tablets, again, units of work that we distribute through the cluster. The place where we distribute them is into tablet servers. So here in the middle of our diagram, we have a bunch of tablet servers that are hosting tablets, and client processes or applications on the right-hand side there are basically interacting directly with the tablet servers to do reads and writes to those key spaces. On the back end, you've got master processes that deal with load balancing and garbage collection and making sure everything stays online. We've got HDFS, which is used to store our data and also store our write-ahead logs. We'll talk much deeper about that. And then Zookeeper that's there to provide a quorum consistency model and basically is kind of the root of stability in our cluster. Mostly what we're going to focus on here is the interaction between tablet servers and client processes, so the write path. And we're going to do a little performance modeling on that. So let's zoom in a little bit here. A client, when you write a client and you're streaming data into Accumulo, you use something called a batch writer. And your application will generate mutations. Right, mutation is, I've got this row, maybe the row is representing a document, and I want to make some changes to the columns in that row. So those all get grouped together into this multi-headed cat dog. And we send those to a batch writer. Right? ingesting into a batch writer, the batch writer batches things, right? Did anybody predict that? All right. Okay, so we take lots of mutations, we batch them up, we put them into a buffer here, and when that buffer fills up, we move it aside, we have a new buffer that can immediately be, we can immediately write new mutations into it, and we take that original buffer and we partition it. Right, so it's kind of like a sort, but we're only really figuring out where these mutations go. Which tablet servers should we send these mutations to? Right, so once they're split up, then we send them via thrift to the tablet servers. On the tablet server side, a batch of mutations will come in. And it'll go through the thrift client handler. There's a bunch of threading stuff in here that we're going to gloss over for this talk. But each of those mutations then gets split up into the keys that it represents and into a write-ahead log entry. Right, so we take that group of mutations, each mutation into it. In it, we create the key value pairs, write them into the in-memory map. That's so that they're immediately available for query. Since Accumulo is a sorted key value store, we can really only answer queries out of sorted storage mechanisms, and mutations come in effectively in random order. So that in-memory map is there to give us very low latency between writes and reads. It's also volatile, though, so we have to keep track of what's in the in-memory map until that gets flushed to disk. And that's what the write-ahead log entry of mutation is for. Right, so we write that write-ahead log entry. We can basically recover from a failure where the in-memory map goes away. And at some point, we have a little acknowledgement here that the write-ahead log entry has been written. So we tell the client, yeah, I've got that data. You don't need to hold on to it anymore. And that's actually done per batch. So the whole batch of mutations gets a write-ahead log synchronization event there. There's other operations here. So the in-memory map can fill up. We write our files from that, and we do a bunch more operations in the write-ahead log to basically keep that journaled approach where at any point, if something fails, we can recover from it, and we know exactly what's going on there. So this journaling, it induces a lot of load on the write-ahead log, and the load there in particular is syncs, disk syncs. Right, so we can stream data to a file pretty quickly. Once we start syncing it, those are expensive operations. So we're going to look very deep at how those operations work. From a general setup here, we're looking at a performance model that's oriented towards weak scaling. So I want to keep a constant problem size per server, meaning that if I have one server and it's doing X amount of work, I have two servers, they're doing 2X amount of work, 4 servers, 4X, and so on and so forth. Accumulo is designed at its core so that we can scale up horizontally like that. So with this performance model, we're going to look at some of the elements that are in there that make it challenging, and some of the bottlenecks that we're going to hit next as we continue to try to scale. The type of load that we're going to look at here is continuous ingest style load. Right, so I take a bunch of keys on the clients that I'm writing, create mutations out of them, but create them randomly. So the random keys are going to be uniformly distributed across the tablets. And every client that I have is actually going to write to all of the different tablets. This becomes important when we talk about how do these things get split up and batched, which has effects on the number of synchronizations that we do. We're also going to, just for simplicity's sake, assume that all of our tablets are pre-split. So our tablet servers are already hosting the key ranges that they're eventually going to host. I don't have to worry about dynamic splitting in this particular model. And again, this model, we're going to focus in on the bottleneck of write-ahead log sync operations and how those affect the overall performance. So linear scalability is something that you really want to achieve if you're trying to build a big database, right? And performance is one thing. Linear scalability is probably even better than performance. Accumulo is written in Java. Java probably versus C++ maybe gives away a certain amount of performance. because of the model we use in Accumulo and the fact that we can just double the cluster size, get double the performance, that gives us a very powerful mechanism here. This particular graph is studied by Lincoln Lab. We've got some Lincoln Lab folks in the audience here, so they'll keep me honest. But there was a little bit of cheating going on in this model. What they did was they pre-split all their tablets, and they did local writes to those tablets. So the application knew it was going to the local tablet server when it wrote, and they actually turned off the write-ahead log. So we're going to look at this from the perspective of if you want to generally do this in an online application that needs a write-ahead log and doesn't necessarily have all of the logic to pre-split the input, what do you run into? Okay, so what is a write-ahead log? Really, a write-ahead log in Accumulo, as of Accumulo version, what was it, Eric, 1.4 or 1.5? Is it HDFS? 1.4. Yeah, it was 1.4 or 1.5. Anyway, it's an HDFS file that we're appending to. So every tablet server gets a file. Write-ahead log entries get appended to that. When we synchronize it, we call the synchronize method on that HDFS file. That file is shared across all of the tablets in the tablet server. So we don't have one file per tablet. We have one file per tablet server. The method of synchronization is configurable. So we have two different types that we use. One of those is hflush. Hflush means that, all right, file, all of that data that I've written to you, make sure that it is on all of the servers that are going to write to their local files, or their local disks, hard drives. Hsync is a little bit more extreme, so it says, all right, everybody, all of the servers in this write pipeline, make sure that the data has hit disk on every server. So hsync actually goes down and calls an fsync on the local file system, which it spins the disk to this current location and guarantees that it actually makes it on there. I'm glossing over a lot of details here, but the important parts here are that hflush is, when you call hflush, it's something like a millisecond operation. Right? It's making sure it's in memory on a remote server. Hsync, the way that's implemented, is more like 100 milliseconds to do a single hsync operation. Okay, that'll become important pretty soon. The other thing we do with write-ahead logs is we want to be able to garbage collect them. Right? As soon as we've done that minor compaction operation, taking what we had in the in-memory map and writing it to disk, we no longer need the mutations in the write-ahead log that were associated with that. So we roll over write-ahead logs every gigabyte or so. It's configurable. And when write-ahead logs no longer reference data that's in the in-memory map, we can get rid of them. We just delete them. What we have to do around that is we have to keep track of which tablets are actually referencing which write-ahead logs. So there's metadata there. That metadata gets stored in the metadata table. So if you have maybe 1,000 different tablets, all for the same table, they'll have metadata writes that go to a smaller number of tablets, and we'll look at the effect of that as well. Okay, everybody still with me? Any questions on this so far? All right. So since we're building a write-ahead log synchronization model here, we care about accounting for write-ahead log synchronizations. And I've got two different classes of write-ahead log synchronizations that I'm going to track. One of those is primary write-ahead log syncs. So these are things like when I send a mutation group into a tablet server, it synchronizes and then acknowledges to the client. Tablet definitions are when I write a new mutation, I also write in an element in there that says, all right, for this tablet, I'm going to refer to it as number 1. And for this tablet, I'm going to refer to it as number 2. So those tablet definitions also go into the write-ahead log. And then there are journal entries associated with minor compaction that also go in there. So those are all happening locally on every tablet server for data that tablet server is writing. We have these secondary operations that happen on the metadata table where if I change the write-ahead log set, I have to register those write-ahead logs with the tablets, and that registration happens on the metadata table. The metadata table itself is a bunch of tablets, and those tablets also have a write-ahead log associated with it. So when I make that metadata write, I have to guarantee that that metadata write is durable, so that has to hit disk. So there are these secondary write-ahead log syncs on the metadata table that become very important here. So those things are registration of new logs, clearing unused logs, basically to support the garbage collection of the write-ahead log. There's registration of minor compacted files. There's a bunch of handshaking for major compactions, and there are tablet lifecycle events. We're going to look at most of these things as we do a write-ahead log synchronization model. Okay, so I know you guys didn't come for the cat dog images, but we also have spreadsheets here, so that should appease the rest of you. So we're going to start out with a pretty simple spreadsheet up at the top here. I'm going to define some variables, only 5 variables, it's okay. You'll survive. And then we're going to look at 4 operations that are basically functions of those variables. So my variables for this model are the number of servers, so that's all the servers in my cluster, and I'm going to assume that they're also proportional number of clients. I have T in here, which is the number of tablets per server. So each tablet server is going to host a certain number of tablets. That number is T. We also have some memory sizes and file sizes here. So batch writer, BW, is the buffer size of that batch writer. How many mutations, how much space of mutations can I buffer up before I have to partition that and send it to my tablet servers? There's the in-memory map size. So that's things like how many key value pairs across all of the tablets hosted on a tablet server, how much space of key value pairs can I buffer into memory before doing a minor compaction. And then the write-ahead log size is how many mutations can I write to the write-ahead log before I have to roll over to a new write-ahead log. Okay, so these things are all represented here. From those, we have operations like primary flush rate. So primary flush rate is I send a batch from my client to the server, it flushes that to the write-ahead log and acknowledges it. That's a primary flush. And I can do a simple calculation here that says per byte, I'm going to do S over BW times 2. So BW divided by 2 would be the size of the buffer on the batch writer. So I'm inverting that. So I'm dividing the number of servers by that. And that's basically saying I take that batch writer, I partition it into data for each server, and I send those things to servers. That's how the batch writer works. So with that, you can basically calculate that if I'm storing a certain amount of data, that data is going to get grouped into certain size groups. And each of those basically gets turned into a synchronization operation in the write-ahead log. So that's primary flush rate. Everybody with me so far? Okay, this is important. There's going to be an exam. All right. Minor compaction rate is basically I have a certain number of tablets. As I grow the number of tablets on my tablet server, I shrink the amount of memory that's available for those. That amount of memory that's available for it is the IMM in memory map size. So basically, and this is kind of a rough calculation, but I get a minor compaction rate approximately equal to T over IMM. Write-ahead log rollover rate is a very similar calculation, right? The more tablets I have, the more rollovers I'm going to have because I'm accounting for these per tablet, and I can write, WAL amount of mutations into that write-ahead log. So I'm going to roll over all of my tablets on the tablet server every time the write-ahead log fills up. Okay, everybody still with me? This stuff is really basic, right? Pretty simple. Okay. And then major compaction rate, just as a simplification here, I'm going to assume that I do about 1/4 of the number of major compactions as minor compactions. And this thing varies. You can kind of set that based off of the major compaction ratio. That's another talk. So I'm going to, mostly we're not going to care about major compactions here. All right, so now that we have these rates, we can take our accounting for the various types of write-ahead log syncs, Half of those happen on the tablet server, half of them happen on the metadata, the tablet server hosting the metadata table, right? For apply updates, close updates, that's our primary flush rate. Minor compaction start and minor compaction finish are two different syncs that we do in the write-ahead log. Those both happen at the minor compaction rate. And defining new tablets in the new log, those happen at the write-ahead log rollover rate. When I take those operations and I concentrate them on the metadata table, I have things like registration of new logs, which mirrors the definition of tablet, but instead of doing it once per tablet that's local, I do it for every server. Right, so all of those servers go into the metadata table, and I keep track of the metadata that way. So basically, we have the similar minor compaction rates, major compaction rates, but everything is scaled up by S because of that concentration in the metadata table. We're going to look at a couple of things as we do this. So we'll look at the total number of syncs for doing a certain operation, which will be write a gigabyte of data. And we'll look at the total number of metadata table syncs across a whole cluster if we're writing a gigabyte on each server. All right, so let's look at the simple case here. We're going to set some variables here. I'm going to have one server, 10 tablets being hosted on that server. I'm going to have a batch writer buffer size of 100 megabytes, which is actually the default value. I'm going to have an in-memory map that can hold 4 gigabytes of data and a write-ahead log which holds 1 gigabyte. So these are pretty standard Accumulo settings. From this, we can determine, and we've scaled per gigabyte here, that writing a gigabyte of data means I'm going to do 20 and a half write-ahead log syncs for that primary flush. Right, likewise, we're going to do 2.5 minor compactions. We're going to roll the write-ahead log 10 times here, which is basically one new write-ahead log accounted for with 10 tablets. Right, so each tablet gets rolled once. That's 10 tablet rolls here. And we're going to do about a half a major compaction at that rate. All right, so we can account for those down here, and we can see that if you add everything up, you basically get a bottleneck of syncs, which is you have to do 35 sync operations to write a gigabyte of data to your one tablet server. Okay, so we look at that. We can do a quick calculation. So if I want to write 1 gigabyte of data and I got to do 35 syncs, and each sync takes 100 milliseconds, I can write at 300 megabytes per second according to this particular bottleneck. Right, that would be great. I mean, it's what's the problem, right? 300 megabytes per second. Okay, so let's take some other scenarios here. All right, now I've got one server, and that one server has 1,000 tablets on it. All right, we can do our calculations on that. We can see that now the primary flush rate is the same because that's basically batches on the client side. They didn't change because I'm sending them all to the same server. The minor compaction rate increases, so now we have a bunch more minor compactions, and now we've got to roll over 1,000 tablets instead of 10 tablets. So with that, we get some different calculations down here, and we can see that there's a bottleneck. Now it's on the metadata table because we're accounting for basically those registration of new logs on the metadata table. And with all those other operations, ends up being 1,600 plus syncs to write a gigabyte of data. You do that same calculation. Now with 100 millisecond sync, you're down to 6.6 megabytes per second. Not as good, right? So we want to be able to write, I mean, most Accumulo's instances, tens of megabytes, maybe 20 to 30 megabytes is a good optimized number here. Can't really do that with this type of synchronization. So maybe if our syncs take 1 millisecond instead of 100 milliseconds, now we can achieve 660 megabytes per second with this bottleneck. So that's great. Can we use hflush instead of hsync? Well, maybe you can, maybe you can't. I mean, it kind of depends on your durability setup. In setups where the probability that one server dies, given that another server just dies, is kind of independent. Right? It doesn't change. You wouldn't expect a cascading failure that's going to bring down a bunch of servers, and that tends to be independent battery backups of each rack or of each node. When you have that, hflush is usually pretty fine to use. When you don't have that, you're probably talking about hsync, and you'd be looking for a different solution in this case. We'll talk about that in the next slide. Okay, so let's scale it up a little bit further here. So now we've got 1,000 servers, not just one server, and 1,000 tablets per server. Now keep in mind these are tablets that are being actively written to per server. So basically, we're partitioning our data up into 1 million active tablets when we're doing this. So that's fine. That's not unreasonable. Primary flush rate in that case really increases a lot because instead of our batches being sent to one tablet server from the client, now we're sending those batches to 1,000. So our batches get a lot smaller. So we do a lot more, the secondary operations there. But the other thing that happens here is now we've got a huge inflation of this registration of new logs that happens on the metadata table. So we've got 1.6 million sync operations to write 1 gigabyte per server. So that would be basically writing about 1 terabyte in this case. But we're going to account for things per server because we want horizontal scalability. Now what we're running into is 1 gigabyte divided by 1.6 million. Times 100 milliseconds. Now we're in like 6 kilobytes per second per server, right? And this is danger territory, right? Even if we switch to hflush, we're really only talking about 0.5 megabyte per second per server. So this is a scenario that needs improvement, right? Everybody with me on that? Has anybody seen this happen? Eric has, all right. Careful, Eric, you might be releasing too much info. Just kidding. All right, so let's take a look at what's happening here. All right, so we've got a lot of apply update and close updates being synchronized, and those are things that are happening locally, right? So we've got 20,000 of those for writing 1 gigabyte locally. How do we do that? We can mitigate that by changing a few settings. So we've got our batch writer buffer, and maybe our batch writer buffer, instead of 100 megabytes, we can change that to 1 gigabyte, right? That's going to basically cut this number by a factor of 10, right? So that could be a huge difference here. Right, when we start scaling up to even more servers, maybe you don't have as much memory on the client, so you might have a bound there. So there are other things you can do. Accumulo uses group synchronization. So instead of syncing for each of these 20,000 sync calls, we'll group those up and we'll do one sync for a lot of them, and that basically that batches these operations. So a lot of this is already taken care of on the 20,000 apply updates and close updates. Another way to do this would be to reduce the number of clients, the number of servers that each client talks to. And again, in the MIT case, this is what they did. They wrote to the local tablet server only from their clients. Sometimes your applications can be parallelized that way. Sometimes they can't. So it kind of depends on the application. We also do registration of those tablets locally. Some of these things, maybe you don't even need to do it, right? So why do you sync on defining a tablet in a new log? That entry doesn't matter until you do another sync of data, right? So some of these things maybe we can skip. So we can patch the code to say, just don't do that. We don't need a sync here. Other things like registration of new logs, there are a couple of ways to mitigate that. So we can split the metadata tables. So don't think about this as one tablet. Maybe our metadata table actually has 100 tablets, right? So we can do that 100 times faster. That's one way of doing it. We can also batch metadata updates. And this is something that the code doesn't do yet. And I think, Eric, correct me if I'm wrong, but the latest patch doesn't do this either. It does it differently. So we'll talk about how that actually works, I guess. But that becomes your bottleneck. And in fact, the 250,000 clearing of unused logs and all these other things also become pretty big bottlenecks. Okay, so what does this mean? This means that sometimes you get some pretty funky performance with Accumulo. So has anybody ever seen a performance graph that looks like this? This is the Accumulo monitor page. So I see probably like half of the audience members have at least some glimmer of recognition in their eyes here. What's happening here is that as we're writing a bunch of data, we're chugging along at 40 megabytes per second. and then we hit a brick wall and we stop. And this is where we're registering a bunch of new write-ahead logs before we can write to those tablets, right? And then we pick up again, and we got to register again. So all of these things are write-ahead log rolling over. There's a secondary thing here, which we see kind of a bimodal. That's also a very interesting topic, but we're not going to go into that here. So one of the things that's new in the code that will be in 1.7 is Accumulo 3423, which is speeding up write-ahead log rollovers. A big thing that this does is it pre-registers write-ahead logs. So rather than having that big dip in the middle of your write pipeline, you do that work in a separate thread, and you basically manage the latencies in that separate thread while you're doing the throughput in your primary write thread. So you get a nice before-after here, where before we have all these big dips, after you get much smoother performance. What else is happening here? So we've got the real question after this is, did we solve the problem, right? So did we actually eliminate this bottleneck? And how far can we scale after this? And I think that's kind of somewhat of an open question. We've definitely seen that it improves performance a lot. But going back to this kind of rigorous performance model that tells you where your bottleneck is and how you can affect it is very important when you're doing performance improvements like this to know how far is that performance improvement going to take you, or is there another thing that you could do to really take it a lot further down the road. So I think we have a lot of future performance improvements to do, specifically around the write-ahead log syncs. Those are things like reducing the total number of syncs, cutting out the unnecessary ones and batching things better. There are also application level things that you can do, like using a design pattern that reduces the actively written tablets. Right, so instead of, maybe your tablet server is hosting 1,000 tablets, but if you're only writing to 10 of them, then you don't have this bottleneck problem. Right, so partitioning data instead of kind of a naive partition, maybe you partition by time, and you're only writing to some portion of that data when most of your data is coming in, at a certain time. So we use that a lot. We use that technique a lot. There are other crazy things that we might do in the far future when we're scaling up to tens of thousands of servers. Things like doing a fat tree topology for our ingest. Right, so on the right here, you can see that there's this clients are writing to servers, but instead of writing directly, they're going through cutoff nodes, and those cutoff nodes are going to be kind of rebatching. This is a technique that's used in a lot of low-level networks in supercomputing, and has been employed there for decades. Maybe there's some options to throw something like that into the application layer around Accumulo, or into the batch writer framework, perhaps. So with this, basically, instead of having a client write to all servers, you have a client writing to the square root of the number of servers. So you get a much better scaling function there. Again, projects, if you're interested in taking up a project like this, talk to me or talk to some of the other Accumulo committers, and we'll be able to help you out. So reducing the data syncs is one thing. Reducing the metadata syncs is through maybe better batching of updates. There's also an option here where instead of assigning logs to tablets directly, we assign logs to tablet servers, and we assign tablets to tablet servers, and then we chase the pointers that way. That's, taking an approach like that could really reduce our metadata operations for dealing with write-ahead log roles. Okay, and the last message I want to leave you with here is that when you see a performance curve that looks like this and it has a bunch of big dips in it, don't assume that Accumulo is just supposed to perform like that by design. There are a lot of these things that have been evident in people's usage of the system. Raise a flag, right? Submit a ticket. We're always looking for ways to improve these types of performance, and a lot of times, your application might hit on one of these things, differently than other applications. So we want to be able to help you out in those cases as well. Okay, and with that, I'll take some questions. Yeah, there's two elements here, right? We have to acknowledge per batch, and our batches are basically sized by, I got to take a buffer of data and break that into batches for each server. In the case of the cutoff, now I break it into batches for each cutoff, and as a client, I talk to basically a square root of the number of servers as cutoff nodes there. So I can make bigger batches and send them. The cutoffs can then aggregate those and send them to the servers and kind of resort and remerge. And then they also have bigger batches. So there's a trade-off here. You've got your extra level of abstraction, but at the same time you can make bigger batches. That's kind of one side of the house here. The other is if you get down into the networking layer and you've got n-by-n connections that have to be made. That's a lot of TCP/IP traffic that is just dealing with keeping those connections alive. So the cutoff, you could reduce that number as well. Again, this is future work. It's kind of theoretical. We could improve these numbers as we hit these bottlenecks. When we're really scaling much larger. Right. So when you hit a batch writer bottleneck, when you decide to bulk import, and the answer to that question is really application dependent. Some applications are going to have very low latency requirements where you want to get data in and be able to query it within tens of milliseconds. Others, you don't really care so much about that latency. So, going with a map-reduce process that batches things differently might be, improvement on it. So I would say, it's not. I can't give you, just a direct answer on that one. Oh, it does. Okay, awesome. So some of this work is already done, and you should be. You see it in 1.7, which will be released. It's right around the corner. A few weeks, maybe. Yeah, and in fact, that kind of gets to this other element of performance that you see here, where it's kind of like dipping. There's, and that's kind of related to write-ahead log block size versus write-ahead log size. There's some trade-offs in this space as well. All right, so if you had, for example, terabyte size write-ahead logs, that would be pretty extreme. You wouldn't have to worry about them rolling over because your disks would fill up as your write-ahead logs filled up, basically. On the flip side, you wouldn't be able to garbage collect those except in chunks of 1 terabyte. So that starts to be pretty expensive. And if you look at some of the life cycles of things like metadata tablets versus other tablets, since all of these tablets are writing to the same write-ahead logs, they have different life cycles of minor compactions. So you might have a metadata table that's kind of, or metadata tablet that's referring to a write-ahead log that's further back in the history, and you might have to keep this stuff around even though a lot of the data has been compacted away. So 1 gigabyte's a pretty good size for balancing some of these other life cycle concerns. But a bigger write-ahead log could alleviate some of the issues. Yeah, in this particular one, we tracked this down into HDFS just behaving very strangely when you use block size of 2 gigabytes or more. And it was just, there was no explaining it. It's just a bug in HDFS. Probably one they're not going to fix because the standard use case is use smaller block sizes, right? Hundreds of megabytes maybe. Have we looked at the trade-off for increasing the block size of write-ahead log blocks and other blocks for Accumulo specifically is the question. HDFS block sizes. And of course, HDFS is used for both the write-ahead log and the R files that we write there. We've looked at some of that. A lot of the block size elements have to do with how much accounting do you do in the HDFS name node. So smaller block sizes mean more block references that are tracked. So the real bottleneck there is operations on the name node. I tend to favor larger blocks, or at least I did until I saw that sometimes they get kind of pretty funky performance here. So gigabyte size blocks are pretty good, and that's bigger than the standard. That'll let you scale to a pretty big number. The other thing that happened more recently than that analysis was that Accumulo can now support a federated approach in HDFS where you can have multiple name nodes. So that helps things as well. Did you have a question, Eli, or are you telling me that my time is up?
Time for lunch.
Time for lunch. All right. Well, thanks a lot, folks.